Okay, you all welcome to finite element analysis lecture. Okay, then last class we discussed how the Galerkin method brought into the finite element analysis procedure. Okay, when the Galerkin method brought into the development of finite element procedure, what we are doing? We are dividing considering domain into a subdomain called elements. Okay, for each and every subdomain we are defining approximate solution. Okay, then we are applying Galerkin method for each and every subdomain to minimize the error. Okay, then we can obtain the better accurate approximate solution for each and every subdomain. Okay, so what we are doing in previous method, then we define approximate solution for considering entire domain, but when it comes to development of finite element analysis, what we are doing, we are discretizing the domain to elements called elements, then we are defining piecewise approximate solution. Okay, that means piecewise approximate solution valid only for considering subdomain. Okay, then we apply the Galerkin method to find the best approximate solution which minimizes the total error. Okay, so then we assemble all of these equations to obtain the global solution. Okay, finally we end up with the set of simple algebraic equations. That means the complex engineering problem, complex differential equation, we end up with the simple algebraic equations. Okay, then by solving these algebraic equations, by substituting the boundary conditions and simplifying, solving the algebraic equations, we can get the approximate solution, better approximate solution for our complex engineering problem. Okay, that is the main idea about this, how this Galerkin method brought into the development of finite element analysis. In the last class we discussed in detail about these things. Today's lecture is mainly focusing. First of all, I am going to explain. I am going to do the example problem related to this one, and I am going to explain how this method is applied to the simple bar element. Okay, structural bar element. How we can develop finite element model for simple structural bar element. Okay, let's continue today's lecture. Okay, this is the example problem we are going to discuss. Use Galerkin's method to formulate a linear finite element for solving the following differential equation. Okay, this is the differential equation is given. Then this is the differential equation is defined in between this region x greater than 1 or greater than 1 and less than 2. Then the boundary conditions are given. Y x is equal 1, that is equal to 0, y x is equal 2, that is equal to 0. Then for this differential equation, we are going to formulate the finite element model to simplify this, to obtain the solution as the form of simple algebraic equations. Okay, let's see. Before going to the formulate the finite element model, I'm going to find the exact solution. The very simply we can obtain the exact solution for this differential equation, then we can compare the obtain exact solution with the finite element solution. So first of all, I'm going to find the exact solution for this problem. Okay, then how to find the exact solution for this problem? How to find the exact solution for this problem? In this differential equation, this part, that means x d2y dx square plus dy over dx minus 4x into 0. Then this part we can write in this kind of form. That means for this that means if you take the derivative of this term, dx dy over dx, derivative of entire. So what is the solution for this one? The multiplication of derivative of multiplication of two expressions, the x and dy over dx, then x d2y dx square plus dy over dx into dx over dx. Okay, dx over dx, that is equal to 1. That means x d2y dx square plus dy over dx. You can see this term here, this term is equal to this term. So instead of this term, I am going to put this one in order to obtain the analytical solution for this problem. Okay, so let's see if we substitute this term instead of this term, I am going to substitute this term. Then we can write this equation in this kind of format. Okay, this kind of format. Okay, the dx dy over dx minus 4x is equal to 0. Okay, the equation is same. So then by separate, I am going to take this part into right hand side. Dx dot dy over dx is equal 4x. I am by separating the variables also dx. Okay, to find the by separating the variables, I am going to integral this equation in order to find the analytical solution for this one, taking the integral. So then in this side we are remaining x dy over dx is equal 4x square divided by 2 plus the constant, integral constant. Then by dividing the entire equation by x, because x is not equal to 0, there is the x is in between the range 1 and 2. So dy over dx is equal 2x plus 1 over x into c. Okay, again I am going to separate the variables. Dy 2x plus 1 over x into c into dx integral. So here we are having the solution y. So what we are having here, 2x square divided by 2 plus here is a constant, the 1 over x. What is the integral? ln x c. Let's take this constant as c1. Here the c1 plus here again we are having the another integral constant, the c2. Okay, c2. So then the final solution we can write by simplifying this equation, the yx is equal x square plus ln x c1 plus c2. This is the final solution we obtained for this by simplifying this problem. So then we can go for to find the unknown constant, the C1 and C2 behind the boundary conditions. By substituting the boundary conditions, we are going to find the unknown C1 and C2 constant in this exact solution. Okay. Then y x is equal 1, y x is equal 1, that is equal to 0. Okay, in this equation x is equal to 1. Here is 1 plus ln 1 c1 plus c2. Okay, so then this term is equal to ln 1 is equal to 0. That means we are from this equation we are obtaining the c2 is equal to minus 1. Okay, c2 is equal to 1. So then by substituting the second boundary condition, x is equal to is also equal to 0. 4 plus ln 2 c1 minus 1. Okay, so then minus 1, here is 3 minus 3, the c2 is equal minus 3 divided by ln 2. Okay, so then this constant I am going to substitute in the differential equation. Then the yx exact solution, you can write x square minus 3 divided by ln 2 ln x minus 1. Okay, this is the exact solution for this problem. Okay, for this differential equation, this is the exact solution. Okay, exact solution. Let's see what is the curve of this exact solution. What is the shape of this exact solution? Let's see. Okay, in order to find the shape of this curve, let's see what are the maximum and minimum values for this equation. Let's see. I am going to derivate an equal to 0 in order to find the whether there is a maximum or minimum values for this differential equation. Okay, dy over dx is equal 2x ln x derivative of ln x, that is equal to, here it is minus 1 over x 3 divided by ln 2. Okay, at the maximum or minimum values that will equal to 0. Okay, 0 at maximum or minimum values. Okay, at maximum or at max or minimum, that is equal to 0. So then the 2x minus x ln 2. So then by taking the into one side, by making x into subject, we are getting 3 divided by 2 into ln 2 in the square root. Here it is plus or minus, plus or minus, but we have taken the positive because x is defined in between range x is greater than x and less than 2. So then I am getting the plus sign only. So then here at this x value, the curve having the maximum or minimum value, to check, to ensure whether it is a maximum or minimum, so I am going to take the second derivative of this equation. Okay, second derivative of this term. And if we take the second derivative to ensure it is a maxima or minima, by taking the second derivative d2y dx square is equal to plus 3 ln2 x square. Okay, this is the second derivative. You can see the second derivative here is plus sign here, ln2 also plus this x value for that is positive value, always the positive value. d2y dx square is greater than 0, so that at this x value curve having the minimum, at this x value curve having the minimum. So by substituting this value, actually you can use your calculators to find the x value for this answer. That is equal to 1.471. Okay, at this x value having the minimum, curve having the minimum, then minimum also we can find by substituting this x value in this equation. If we can substitute y x is equal 1.471, then you can use the calculator to find that one also. It is equal minus 0.5066. Okay, this is the minimum value. So then let me draw the curve for this equation. This is y, this is x-axis. So then here it is 2, here. At x is equal 1, let's take x is equal 1 here, x is equal 1. So then this at 1 point closer to 1.5 here, 1.5 here, something here, having the minimum. Minimum value is equal to minus 0.5066. Let me draw the curve. Okay, here we are having this is the exact solution. This is the exact solution we are having for this problem. Okay, then let's see how to formulate the finite element model to obtain the closer approximate solution for this differential equation. Okay, then I'm going to consider to develop to finite element model. I'm going to consider two elements. Okay, I'm going to discretize the considered domain to a two element. Okay, then this is the considering domain. X here is 1, here it is 2, 1 and 2 x value. Then I am going to discretize the domain into two elements. X value is equal to 1.5. X value is equal to 1.5. Okay, then let's put these coordinates. Later we can substitute these values. X1, Y1, X2, Y2, X3, Y3. Okay, element 1, element 2, node 1, node to node 3. Okay, this is the finite element. This is how we are discretizing the considered in domain x domain to a subdomain to form the elements. Here we are in the two elements. Then the y1, y2 and y3 are nodal values at these points. Okay, so then the approximate solution, I am going to use the linear approximation. So the approximate solution we can write this kind of format. In the last class also we discussed how to write this approximate solution and the linear approximate solutions. The piecewise approximate solution we have to write. So then how we can write that one? x2 minus x2 minus x1 into y1 plus x minus x1 divided by x2 minus x1 into y2. This is the approximate solution we are defining for this range. That means x1 is greater than or equal to, less than or equal to x2. Okay, in this region for the first element, this is the approximate solution we are defining. Okay, for the second region, second subdomain, this is the approximate solution we are defining. It's minus x2 by 3. This is valid for x2, x3. Okay, this is the way we are I'm going to use the linear approximate solutions for this domain. These are called nodal values at the nodes, nodal values. Then this is called trial functions. These are called trial functions. There are two trial functions and the nodal values. The field variable values at the nodes y1, y2 and y3 are called the field variable values at the nodes. The field variable value, means here it is a y. Okay, y value at the nodes. Okay, then this set of equations we can write in a general format. Y star x is equal in 1x. These are called the shape function. Let's take better to put this shape function for element 1. This is for element 2. This is the equation we are defining approximate solution for this problem. Okay, approximate solution for this problem. Okay, here then we are going to apply the Galerkin's method to find the best suitable solution and to minimize the total error associated with these equations. Okay, so then I am going to consider the what happened in Galerkin methods. Consider the entire domain, integral entire domain, Wix into Rx is equal to 0. This is the basic equation in Galerkin method. The way as the weighting function, we are using the derivative of approximate solution with respect to each variable. Okay, each variable. That means when we are derivating this. For example, if you take this solution for this region, if you derive with respect to each and every unknown constant, that means these y1 and y2 variables, we are getting this one as the weighting function, this one as the weighting function. Here we have the two weighting functions wi when you are derivate with respect to y1 and y2 by taking the partial derivatives. Okay, this is the Galerkin equation. So I am going to put these values in this Galerkin equation, the domain. What is the domain? First we are going to consider the first element, subdomain. So our domain is x1 to x2. So then ni, so I am going to put the ni. Then what is the approximate what is the differential equation? Okay, here also I am going to use this one. Okay, then d over dx x dy approximate dx minus the 4x is the differential equation into, sorry, here it is dx d5, yeah, dx is equal to 0. Okay, this is the trial function, this is the residue, and this is I is equal to 1, 2. We have in the two equations. Okay, then we can further simplify this equation. For the second subdomain also we can write at the same time I am going to write that second subdomain equation, x2 to x3, second subdomain equation, again the ni d over dx, same equation, similar equation, y star dx minus the 4x into dx is equal to 0, I is equal 1, 2. Okay, for the second subdomain, the Galerkin, by applying the Galerkin equation. Okay, then let's see how to further simplify this equation. Okay, then if we take the derivative of this term, if we take the derivative of this term d ni x dy over dx what we are getting? We are getting ni dx dy over dx plus x dy over dx into dni over dx. Okay, so then by making this term into this side, so we can write d ni x dy over dx minus x dy over dx dni dx is equal to ni dx dy over dx. Okay, so that means instead of this term, in this equation, Okay. Okay. Here you can see this is the equation previously obtained. Instead of this term, instead of this term here, I am going to put these two terms in here. Okay. The instead of this term, I think. Okay. In this equation, instead of this term, I am going to put these two terms in this equation. Okay. Okay. Then let me write the equation after putting these two terms in this equation. Integral x1 to x2 d ni x dy over dx dx minus x dy over dx dni dx minus now equation ni the 4x into dx is equal to 0. Here I is equal 1 comma 2. Okay, 1 comma 2. Then we can further simplify this equation. Here if we take the derivative of this term, we are getting ni x dy over dx, the limits x1 to x2. In this equation, this term I'm going to here it is a minus integral x1 to x2 the 4x ni dx. This time I am going to take to a right hand side the integral x1 to x2 x t ni dx into the here it is approximate solution. So then what is our approximate solution? Our approximate solution is equal to d n1 y1 plus n2 y2 dx into dx. Here the ni here. So then I am going to apply boundary conditions here. So I am going to write this one in this side. Okay. Integral x1 to x2 x d ni dx, derivative of this term here, the y1 and y2 are constants values, the field value at the nodes. So then d n1 dx y1 plus d n2 dx into y2 we can write in this kind of format. Okay, then ni x dy over dx into x1 to x2 minus I will write that down, x1 to x2 4x ni dx. Okay, finally our equation is simplified to this kind of format. You can see. Okay. For I is equal 1. For I is equal 1. I am going to write the equation for I is equal 1. Okay. For I is equal 1. Okay. For I is equal 1, the integral x1 to x2 x, the derivative of first shape function, derivative of first shape function is consider the first domain and the first shape function n1. What is the derivative of this one? Minus 1 divided by x2 minus x1. Okay. So the derivative of first shape function into minus 1 divided by x2 minus x1 into derivative of first shape function minus 1 x2 minus x1 into y1 plus derivative of second shape function. Here is constant, so then in 1 divided by x2 minus x1 into y2 into dx is equal to first shape function. What is the first shape function? X divided by x2 minus x1 into x into dy over dx, approximate solution, into x1 to x2 minus this term integral for integral x1 to x2 x, what is the first shape function? X2 minus x divided by x2 minus x1 into dx. Okay, then this is the our equation by considering the first shape function. Okay. We can further simplify this shape function. I am going to take x2 minus x1 square 1 over x2 minus x1 square out from this equation. Okay, then we can write this equation. So it is square integral x1 to x2 x y1 minus y2 into dx is equal, then here if we can substitute the boundary conditions, if you substitute x2 in here, so what happens if you substitute the x2 boundary condition, this one goes to 0 because this term is equal to 0. If you substitute the x2 boundary condition, this term goes to 0, that means the entire expression goes to 0. Only we are remaining the x1 term. If you substitute the x1 term, this term become 1. So then we are remaining then x1 dy over dx. Then we can write that one minus x1 dy over dx, the limits x1. Okay, that means for this dy over dx term we have to put the x1 limits. Then the 4 x1 to x2 x2 minus x2 minus x1 into dx. Okay, this is for I is equal 1. Then the for I is equal 2, you can write the equation. By looking at this equation, we are able to write that equation. For I is equal to, what is the value? x2 minus x1 into square integral x1 to x2 x here y2 minus y1 dx is equal here x2 dy over dx. Here is approximate solution. Integral minus 4 x1 to x2 x into x minus x1 divided by x2 minus x1 into dx. For I is equal to, for I is equal to. By looking at this set of equations, we are able to write the domain considering region x2 is greater than x and less than x3. The two equations we can write by looking at these equations. What you are getting? Again, same for I is equal 1 for this region. 1 over x3 minus x2 into square integral here x2 to x3. In this time region is x2 to x3 x y2 y3 minus y2 into dx is equal minus x2 dx over dy over dx x2 minus 4 x2 to x3 x3 minus x divided by x3 minus x2 into dx. Then the for I is equal to, for I is equal to also we can write that equation for second subdomain. For second subdomain, the 1 x3 minus x2 into square integral x2 x3 x y2 minus y3 dx is equal x3 dy over dx x3 minus 4 integral x2 to x3 x minus x2 x3 minus x2 into dx. Okay, then these are the equations, the four equations we obtained because we are in the four trial functions. Then and the two subdomain. This is the first subdomain. Two equations for consider the two trial functions. The two trial functions. Then this is the subdomain x2 to x3 obtained consider the two weighting trial functions. Okay. In these equations, we can simply simplify this term. We can obtain this value for this expression. Let's take this one as the by doing the integral and using the calculator, we can obtain the value for this equation. Let's take f1 1. Let's take this is f2 1 for this expression. So then this one f1 so yeah, f1 second region, second element, F2 second element. Okay, so then if we take this term, then let's see how to simplify that term. F1 1 is equal minus 4 integral x1 to x2 x2 minus x2 minus x1 into dx. This expression also we can write in this by substituting these x1 and x2 values, because our values are x1 is equal to 1 and x2 is equal 1.5. Then x 1.5 minus x 1.5 minus 1 into dx. Then to simplify this, to obtain the value for this expression, you can use your calculators. I have already found that value, that is equal to minus 1.6667. Okay, 667. Same as for F2, F21 also we can obtain, for this expression also we can obtain the value, that is equal to minus 1.333. For this expression also we can obtain the value F12, that is equal to again 1.6667. F22 also we can obtain, that is equal to minus 1.8333. Okay, then I'm going to substitute this then at the same time we can simplify this expression also. This expression also we can simplify. Let me simplify that one also. If you take this expression separately, I'll do it on separate paper. Okay, for this expression what is x2, that is equal to 1.5, no, 1.5, x1 is equal to 1 into square integral 1 to 1.5 x y1 minus y2 into dx. Okay, this is the expression, the equation. So then this one we can simplify, that is equal to 0.25. Then only these are independent from the x. So then x is square divided by 2 into 1 to 1.5 y2 minus y1 minus y2. Okay, so then we can if we can simplify this equation, we are getting 2.5 into y1 minus y2. Okay, for this step. Okay, then for this term we are getting that one. So then here also we are getting, for this equation also we are getting 2.5. Here also we are getting 3.5. Yeah, 3.5. Here also 3.5. So then I will write that set of equations we are obtaining. Yeah. For the first equation, let me write the subdomain. Subdomain x2, that means that value is equal to 1.5. For I is equal 1, we can write the equation 2.5 y1 minus y2 is equal minus x1 sorry, again we can write for x1 is equal to 1. Okay, 1 dy over dx into x1 minus f1. What is the f1 mean? Okay, minus 1.5 1.1667. Okay, yeah, okay. Then for the second, for I is equal 2, they are getting 2.5 y2 minus y1. Here now it is 1.5 dy over dx into x2 minus this term 1.333. Okay, and this is the set of equation for first subdomain. Then for the second subdomain x3, that means 1.5 2. For I is equal 1, 3.5 y2 minus y3 is equal, this time minus 1.5 dy over dx into x2 minus 1.6667. Then the for I is equal to 3.5 y3 minus y2 is equal, in this time it's equal to 2 dy over dx into x3 minus 1.8333. Okay, then these are the four equations. We end up with the simultaneous equations, set of simultaneous equations. Our solution is simplified to the set of simultaneous equations. Okay, set of simultaneous equations. So then these set of simultaneous equations we can put into a matrix form. Okay, we can represent all of these simultaneous equations on a matrix form. Okay, let me represent this simultaneous equation in a matrix form. For element 1, these are the equations. This set of equations I am going to put into the matrix form. 2.5 minus 2.5 minus 2.5 2.5 y1 y2 y1 y2 is equal to minus 1.6667 minus dy over dx into x1 minus 1.333 plus 1.5 into okay, in the previous one, this one should be positive. This one should be positive because this one should be positive. Here it is positive. Here also positive. Okay, this one should be positive. This one should be positive. So it is positive. So then dy over dx into x2. This is element 1 equation. For element 2 equation we can write 3.5 minus 3.5 minus 3.5 y2 y3 minus 1.667 minus 1.5 dy over dx into x2 minus 1.8333 minus plus 2 dy over dx into x3. Then you can see the two simultaneous equations. Our solution is simplified the two simultaneous equations. Two simultaneous equations. Okay. Then this set of simultaneous equations also we can write. I will write that one also. The four simultaneous equations we can write. 2.5 y1 minus 2.5 y2 is equal minus 1.1667 minus dy over dx into x1 is the first simultaneous equation. 2.5 y1 plus 2.5 y2 is equal minus 1.333 minus plus 1.5 into dy over dx into x2. 3.5 minus 3.5 into y3 is equal minus 1.667 minus 1.5 dy over dx into x2. Then minus 3.5 minus 3.5 plus is equal minus 1.8333 minus plus 2 dy over dx into x2. Okay, these are the four simultaneous equations we obtain. We end up with these four simultaneous equations as the solution of this differential equation. Then all of these equations we can put into we can assemble to obtain the global solution. We can assemble into a global solution. Let's take this equation as equation 1, equation 2, equation 3, equation 4. So I'm going to add equation 2 and 3. If we can add 2 and 3 to everything, these two minus 2.5 into y1 plus 6 y3 minus 3.5 into y2, it is y2, y3 is equal minus 3. Let's take equation 5. Then all of these equations we can put into a single equation called the global equation. So I'm going to put all of these equations in a single equation That means I'm going to assemble this equation to obtain the global equation. Okay. The global equation y1, y2, y3, then the terms of this global equation minus 1.6667 minus dy over dx into x1 minus 3 minus 1.8333 plus 2 dy over dx into x3. Okay, then we can put these values 2.5 2.50 minus 2.5 6 minus 3.50 minus 3.5 3.5. Then this is the global equation. The global solution is called the global solution. The global solution. Then for this global solution, what we are going to next, what we are going to do, we are going to apply the boundary conditions in order to find the unknowns. Okay, so I am going to put the boundary conditions. What are the boundary conditions? Known values of the at the boundaries, the y1 and y3 are equal to 0. That's given. 2.5 minus 0 minus 2.5 6 minus 3.5 0 minus 3.5 3.5. Then 0 y2 and the this one also 0. Okay, then these values you can evaluate. Yeah, then dy over dx, yeah, if you can obtain the then this one minus 1.6667 minus dy over dx x1 minus 3 minus 1.8333 plus 2 dy over dx into x3. Here you can see we are having the three equations and the three unknowns. Then this is the unknown and these are unknowns. Then we have three equations that we can simplify this equation to find the unknowns. Then first I am going to find this unknown. Okay, what is the equation? Yeah, then we can find this unknown here. Here we are having the three unknowns and three equations. By simplifying these three unknowns and three equations, you can find these unknowns. That means the three simultaneous equations we are having. Okay, three simultaneous equations we are having. By simplifying this simultaneous equation, we are able to find these three unknowns. So I'm not going to do that calculation. I just write these values. That you can try it at home. Okay, is equal minus 0 0.5 minus 0.5. Then dy over dx at the x1 is equal minus 2.3281. Then the dy over dx at x3 is equal minus 1.8360. Then the global equation the global solution equation we can write in this kind of form. After obtaining these unknowns, zero, then minus 3.948 minus 3 1.8387. Okay, after substituting the boundary equation, this is the equation we are obtaining. Okay, this is the equation we are obtaining. Let me explain this solution. Let me explain that solution. We drew that solution. Yeah. Okay, this is the exact solution we obtain. This is the exact solution we obtain. That is this one is equal to, here is 1.47, here the 1.5 we are having the value. So for the 1.5 we are having the value is equal to 0.5, something like this. Okay, if we plot our finite element solution, the approximate solution, we are having something like this. Okay, we are having something like this. Okay, then this is the approximate solution we obtain in a finite element formulation for this problem. If you can increase, you can see, if you can increase a number of elements, number of subdivisions, we can get the better accurate result. If you can, like this, you can obtain the better accurate approximate solution in this kind of procedure. I think you all got a very clear idea how this how to use this finite element Galerkin finite element procedure to solve the differential equation by dividing the considering domain into a subdomains. Okay.